Welcome back to this continuation of MATLAB and how to work out transmission lines in MATLAB. Okay, so in this module, what we look at is how do I visualize all the different kind of waves on a transmission line. Okay, so let's just I've created a new script file. Let's give it a name. So let's say visualize waves on a TL. Okay, let's save this. So let's call this TL underscore visual. Okay, this will really help us to get a feel for what is a traveling wave. Why is it called a traveling wave? What is a standing wave, and why is it called a standing wave? Okay, so we have seen the expressions that are written for a forward wave. So for example, a forward wave, we all know, we write it as the real part of e to the, let's call it j omega t minus kx. This is the kx, sorry. Right, so this is how we write a forward wave, and a backward wave, we write it as the real part of the same complex exponential, except with a plus sign between k and x. Right, now is this we always think about this, the plus sign here and the minus sign here, and to someone it might almost seem like something that has to be memorized, that this is a forward wave with a minus, this is a backward wave with a plus. But is there a more intuitive way in which we can actually visualize this and visualize the forward wave, the backward wave, and the separate standing wave? So in this module, we will make use of and learn a new command in MATLAB, which is called meshgrid. So what is it that we want to look at? We want to simultaneously plot in time and space. So far, all the plots that we have looked at, they are just one-dimensional plots. But now we want to visualize something in some physics that's happening in 2 dimensions. Okay, so the command that we will use for generating this grid of time and space is called meshgrid. Okay, so I'm going to give you a very simple example first. I'll just type it into the command window. So it's the command meshgrid. If you want, you can read all about it over here. This is the detailed long description over here. So meshgrid, so it returns a Cartesian regular grid in 2 or 3D if you give it what is the range in x and y, and it will create these coordinates. Okay, so you can read this help or the documentation by yourself. Let's get our hands dirty, as they say. So I want to create as output, so these are the 2 arrays that will hold the coordinates, and I want to say mesh grid. So I want to create a very simple mesh which has, let's say, 3 mesh grids in the x and 2 grids in the y. Okay, so I will say 1 to 3. We know the meaning of the semicolon notation. So 1 to 3, 1 colon 3 means 1, 2, and 3, and in the y direction, let's just give it 2. Okay, so let's hit enter, and you notice that in the workspace 2 new variables have been created. We can just print them out over here. So you notice that I said I wanted to create a xy grid. In the x direction, I want the coordinates to be 1, 2, 3, and in the y direction, I wanted the coordinates to be 1, 2. Okay, so these can be, it need not start with 1. For example, I want to create a mesh grid that is from -1 to, let's say, 2. Okay, and now if I plot x over here, you can see that it's starting from -1, 0, 1, and 2. Right, so it's up to us. The starting points and the ending points, they need not be integers, as we have seen before. I can also do something like if I wanted a finer gradation, I can do something like this. So now x is going to be of length 7 because there are values at every half integer. Okay, so now let's go back to our original specification, which was this. So I have it in the command history, which is convenient. So I'm just going to evaluate it once more. So that shows me my x has taken these values 1, 2, and 3, and what has y taken? Y has simply taken the values 1 and 2. Okay, so that makes sense because the first output over here, x, this contains the x coordinate. So the x coordinate is ranging from 1 to 3. Let's say 1 to 3, whereas the y coordinate is only ranging from 1 to 2. Right, so if I take a collection of x comma y, I can denote any point in this xy plane using the capital X and capital Y. So we will be using this mesh grid command to create a grid in space and time. Okay, so now let's try to define our wave before we start using the mesh grid. Okay, so let's take some simple units. We know that omega is defined in terms of 2 pi into f, and f is our frequency, which is expressed in terms of the time period as 1 over t. So let's define our time period, capital T. Let's call it, to be for simplicity, let's just call it 1 unit. Okay, so this is the time period. From here I can define my frequency to be 2 pi into 1 by t. That is my angular frequency, right? So angular frequency. Similarly, let's talk about, so I've written k over here because that in our lectures usually we use the word beta. K means the same thing, right? So I'm going to say now, to define k or beta, I need the wavelength on the line. The wavelength on the line can be specified directly, or it, indirectly you may calculate it using the velocity and frequency. So let's keep life simple. Let's assume that the wavelength is given. So let's say lambda is let's say 0.5 meters. Okay, so this is wavelength. Okay, from here we can define k is 2 pi by lambda. Okay, so this is my what we call propagation constant. Okay, let me also write same as beta. Okay, it's just shorter for me to write k instead of beta, which is why I'm writing k over here. Okay, so now let's run this. So now these variables have now been created into the workspace. I have my time period, k, t, and w. Okay, so now what is the spacing in time that I want to visualize? So it's good to take a few integer time time periods so that you can really appreciate the visualization. Okay, so let's create a time grid. So let's put a comment over here, create grid in time. Okay, so let's say that I want to go from t, I can define t is equal to, so 0 to let's take 2 time periods, okay, of y2. Let's take 3 time periods. Okay, now this would create an array only at integer time instance, but I want a much finer gradation than that. So let's make it finer. Okay, so let's, for example, I can define this instead of, I can insert something over here, and this will be the discretization of time. So let's make it something very small. For example, I can do it as 0.1. Right, so this is going to create my grid in time. Similarly, let's create grid in space. Okay, so I'm going to give it the letter x. Again, let's take several wavelengths. Let's take 4 wavelengths, for example. So I want to go from 0 to 4 lambda, but I don't want to be only at integer time, integer spaces in places in space. So let's make this again 0.05. Let's make it even finer. Okay, and let's suppress the output. So let's run this and see what do we get. Right, so it's created a time array which is 31 time instance and a space array which has 41 instances. Right, so these spacings or the grids in time and space, they need not be of the same length. It does not matter. Right, so now it's time for us to use our space time grid. So let's write create space time grid using meshgrid. Okay, so I am going to we like to visualize space as the x-axis, so I'm going to call it capital X. Remember, MATLAB is case sensitive. That means small x and capital X are different, right? So capital X, capital T, this is the output, and I say mesh grid, and I give it the arrays over here, right? So the array is x and t. Remember, previously in my command I had manually specified 1:3. I could as well just copy paste this and put it over here, but it looks a little ugly, so I've created it in this fashion. Let's run it and see once. What happens is small t is as before, capital T now is a 2-dimensional grid of size 31 cross 41, and x is a 2-dimensional grid of the same size. That means I have my space-time grid created in these variables capital X and capital T. Okay, now it's time for us to create the forward wave, right? So the forward wave. Alright, so what we'll do is the forward wave, we've already seen the definition over here. So instead of straight away starting with real part, let's define it as a complex number. Okay, so let's write, so forward is the variable name for it, is going to be a, so let's write this down, is going to be exponential, right? So 1i or 1j, okay, and here is where I need to put omega t minus kx. Okay, so this is what I need to do. Remember that I should give the meshgrid output variables, not the original variables. So let's write down this w, there is t. Oh, actually you notice I have made one mistake over here. So I've used the variable t as time period and as meshgrid. So that is in general a bad idea. So let's just change this t over here, let's call it tp, so that there is no ambiguity over here. Okay, yes, so tp is for time period. Okay, so that there is no overwriting that happens. So omega t minus k space x. Okay, let's run this to make sure there is no problem, right? So it runs fine. It's created a 2D array of the same size, 31 cross 41, but now it's complex value. Excellent. So let's go ahead and visualize this. Remember, we cannot visualize complex numbers, so we have to choose the forward, we have to choose take the real part, I'm sorry, of this function over here. Okay, so the way to visualize this in a very nice graph is to write down mesh, and let's say what is it that we have? We have x comma t. This is what has been given by meshgrid, and let's write down real part of forward. Okay, and before we do the rest, let's write down the x label so that we don't get confused. X label is x, which is space, and the y label is time. Okay, so we can just call it as t. Okay, let's go ahead and hit run over here. There you go. Okay, so now this graph has been produced. It's a three-dimensional graph. There is time on this axis going from 0 to 3 seconds. Okay, let's move this over here. Time is going from 0 to 3 seconds. That's what we wanted, because we had created a time array that was going from 0 to 3 time periods, and time period was 1, so 0 to 3. And x is going over 4 wavelengths. Wavelength was 4, so it goes till 2. Okay. Now the nice thing is that it's very easy for me to manipulate this in 3D. Okay, so if I put this down like this, the time axis is going vertically, the space axis is going horizontally, right? So at the very first sort of look at this, what I should look at is, let's say I keep time fixed. So let's say time is fixed at half. So you can see that this wave, as it goes along x, it has a certain sort of a profile. As time increases, that same phase profile, it moves to the right, right? So you can visualize, you can see this very easily as you keep rotating this. If I make this graph, if I make this plot completely flat like this, right? So now it's flat. I'm looking at it vertically downwards, right? These are the peaks of the wave, and these are the troughs of the wave. So you can see that as the wave is traveling along the x-axis, and as time increases over here, this phase front is moving to the right. So hence it's natural to call this a forward traveling wave. Okay, so this you can visualize it, rotate it in any way, and get a very good feel for it. Okay, so let's let's also give it a title. We can insert a title. So let's call this a forward wave. Okay, I can specify this from the command line also. It's up to us. Okay, now let's create a backward wave. Let's see if it is so obvious what a backward wave looks like. So let's give it a name, backward. Okay, so BKW is for backward wave, and it's going to be very similar to the forward wave, except that the plus is going to get replaced by minus. Okay, all right. Now I want to preserve this old graph, so let's not overwrite it. So to create a new plot, I'll say issue a command figure. Okay, and do the same thing. So mesh x t, real part of the backward wave, BKW. And before we get confused, let's do x label x, y label time, Okay, and let's just give it a title. We set forward wave here, so let's say backward wave. I can go ahead and run the whole script again, but I don't need to. Like, I just want to run this part, so I can highlight this over here, hit right, and say evaluate selection. So it's created a new figure over here. So let's put these two side by side. So this is my figure 1 that I had previously created for the forward wave, and now this is my backward wave. Now notice, let's look at how the troughs are behaving over here, and let's sort of line the forward and backward waves similarly. So you notice over here that as time progresses, increases along this axis over here, the phase fronts are moving in the backward direction. So if I take one phase front, as time increases, instead of moving to the right, it's moving to the left. So this is why this is called a backward traveling wave. Okay, and if I look at it from vertically upstairs, it's what we expected. The phase fronts are moving to the left as time is increasing. Notice the same thing just for revision over here. This is the forward wave when seen from upstairs. As time increases, the phase front is moving to the right. So hence these words forward and backward wave, they're the most intuitive words that you can think of over here. Okay, so this is as far as the forward wave and backward wave goes. Now we know that when we have some kind of a load at the transmission line end, there is going to be a reflection, and as a result of the reflection, there is going to be a interference between the forward wave and the backward wave. Okay, so let's make life very, very simple. Let's assume that I have a perfect reflection of the traveling wave. So let's introduce a reflection coefficient. Okay, so let's call it gamma, and let's call it gamma is equal to, let's just call it 1 for now. Okay, and we can play around with different ways. So let's call this a interfered wave. So let's call it interfered wave 1. Let's give it a name, interfered wave 1, and this is simply going to be the forward wave plus gamma times the backward wave. Right, that's what we want. Now we want to visualize this. So again, let's create a new figure, and then let's do, so I want to do x, t, and I want to look at the real part of this new wave. Okay, and let's write this down over here, something similar. Copy paste this time over here. This won't be backward wave, but this will be interference 1. Okay, as before, I don't need to run it from the beginning, so let's just run it from here. I evaluate selection. Okay, and what have I got over here? Right, so let's see. This is the interference pattern that I've got. This looks very, very different from what I had earlier, right? It's a very beautiful plot. It looks like an egg crate almost. But notice that the maxima and the minima, they are not going, they don't seem to be going anywhere. You know, when I looked at, for example, figure 2 or figure 1 over here, the maxima, they were all, you know, either moving from bottom left to top right, or in this case from bottom right to top left, whereas the maxima or the minima, they seem to be standing still over here. They don't seem to be moving anywhere. So this is a standing wave pattern which has been created, and hence this is called, I mean, the picture itself tells you that this is called a standing wave. Right now, this was the case when I had perfect reflection. I can also have imperfect reflection, right? So let's take imperfect reflection. Okay, so for example, I can say gamma is reflected with an amplitude of, let's say, half, and let's say that as a result of the reflection, there is a phase constant also that gets added. So let's say 1j. Okay, why not, right? So let's call this in INTF2 as the new wave. So this is now gamma backward wave. Let's create a new figure, and let's basically write down whatever we had written down before. Okay, and let's just copy paste this, and let's call this interference 2. Right, so as before, we just need to run this part, and you can say evaluate selection. Let's see what we've got over here. So we've got a wave that looks different from our earlier figure over here. This is, so let's now look at compare interference 1 and interference 2. Okay, so in interference 1, when I looked at it from the top, you notice that there is a difference between these plots over here. There is, in the right plot over here, interference 2, there is, I can see some kind of net movement is happening of these phase fronts to the right along with a standing wave pattern. So right, when I look at this, there is a standing wave pattern for sure, right? But this does not look exactly like, you know, this standing wave pattern. Here the standing wave, the maxima and the minima is absolutely clear, right? There are places where the wave is going 0 and the maxima is, you know, 2, minima is -2. Here the story looks a little different. It looks like there is some part of the wave that is still traveling to the right, but it doesn't look just like a traveling wave. It looks like, you know, a mix of the two, right? And you can see what another difference, the maximum amplitude has not gone to 2 and -2 like it was in this case, right? So this is easy to understand. You can see that because gamma is not 1, what has happened is I can write this expression INTF2 as the sum of, maybe I can just write this down in the comments over here, okay, can be seen as, I can write this as gamma, let's put a colon over here so that you don't get confused. So I can write this, I can add and subtract gamma, right? So I can write this as 1 minus gamma plus gamma times forward plus gamma times backward, right? So you can, now if I take the gamma term, if I take these two terms, then this is what is going to give me a perfect standing wave, and what is left, which is 1 minus gamma times forward, is the forward traveling wave. So it makes sense that this is interference 2 wave that I have plotted over here is a superposition of a perfect standing wave and a remnant forward traveling wave. Okay, so looking at these three-dimensional plots, we really get a good sense for what is happening over here. We know that the voltage and the current both are formed out of interference of the forward wave and the backward wave. So we can expect that at any given time or at any given point in space, there is going to be a standing wave formed for the voltage and current. Okay, so this is again a powerful way in which MATLAB helps in our understanding of wave phenomena on the transmission line.